Solutions and colloids. Solutions are substances which are homogeneous mixtures of two or more pure substances. They are clear, which means that you cannot see any sort of cloudiness to the solution. They are transparent, which means that light will pass through the solution. They do not separate upon standing, which means if I let it sit around for a long time, they're not going to form more than one phase. And they are uniform throughout. The solute is the component of the solution which is present in lesser quantity and is what is dissolved. The solvent is generally present in greater quantity and is what does the dissolving. Substances will dissolve with or without a reaction. You can have instances, for instance, like sodium, which will react with water and dissolve, forming sodium ions and hydroxide ions with the production of hydrogen gas. This is an example of a dissolution that actually reacts with the solvent that it is dissolving in. Sodium chloride, on the other hand, will simply dissolve in water, splitting or dissociating into sodium plus and chloride minus ions with no actual reaction with the solvent that it is dissolving in. Associated energy changes with dissolution are referred to as heats of solution. So the amount of energy that is either absorbed or given off in the course of this dissolution process is what we call this heat of solution. Heat of solution for a negative, which means that it releases energy, is an exothermic process. So if the delta H solution is negative, this process is favored. If the delta H solution is positive, this process is endothermic, taking in energy, and is overall disfavored. Now, solubility depends on a number of factors. Solubility is the degree to which a solute will dissolve in solution and is related to the overall strength of attractive forces within the solution. If there are strong forces that hold the solute and the solvent together, this will tend to favor dissolution of the solute and make a soluble substance. Weak solute forces, which means that the solute itself is not not bound tightly to itself, tend to also favor dissolution. Weak solvent forces, just like weak solute forces, will favor dissolution. So what we see in the first instance is a relatively high adhesive force between the solute and the solvent. With the second and the third, we have weak cohesive forces between the solute and itself and the solvent and itself, respectively. In general, then, the stronger the adhesive forces are versus the cohesive forces, the more the dissolution process will be favored. If a solvent-solute is greater than or equal to the solute-solute and the solvent-solvent interactions, it will tend to form solutions. If the strength of the solvent-solute interactions are less than the strength of the solute-solute and the solvent-solvent interactions, they may not form a solution. Whether or not it does depends upon the overall difference, just how much less the solvent-solute interaction is than the other two combined. Now, dissolution is also favored by increasing disorder in the solute or the solvent. If I mix two things together, the overall measure of disorder is increased. Something that is a mixture is going to be more disordered than something which is a uniform single substance. This process of favoring disorder or favoring a count of possibilities is referred to as entropy, which we'll talk about more later on. Dissolution energies are the energetics that are involved in this actual dissolution process. Dissolution energetics rely on two factors, what we call crystal lattice energy and the heat of solvation. Crystal lattice energy is the amount of energy that is released by a substance forming a crystal. So this is the energy that is given off the stability that comes from forming the crystal. I have to input that amount of energy in order to actually split the crystal apart into its component form. The heat of solvation is the energy that is released by the actual dissolution process. So the interaction of the solvent and the solute together, the energy that is released by this interaction is the heat of solvation. The solvation process is where the solvent and the solute will interact. If I have a solvent that is water, rather than solvation, this is referred to as hydration. So the heat of solution is the difference in energy between the crystal lattice energy and the heat of solvation. If I subtract the crystal lattice energy from the heat of solvation, that will give me my overall heat of solution. And whether or not that is positive or negative depends upon the strength of the crystal lattice energy and the overall heat of solution. Crystal lattice energy is always negative, so the term in the equation is always positive. The greater the crystal lattice energy, the less dissolution will occur, which makes sense because the stronger the crystal lattice energy, the tighter the individual solute particles are binding to each other. A substance will tend to condense as the attractive force becomes greater than the kinetic energy. We know that the attractive force being less than the kinetic energy is in a gas, the attractive force being greater than the kinetic energy is a liquid, and the attractive force being much greater is a solid. So the stronger the overall attractive force, the stronger this crystal lattice energy is, the more likely it is going to be remaining in this condensed form or this structured form. So it takes more energy to get it out of the structured form, either into another phase or into a solution. If the solvent is water, then the heat of solution is called the heat of hydration, in the same way that solvation is referred to as hydration. Writing the term aqueous refers to a hydrated ion. So if I have something like sodium plus aqueous, this is a hydrated sodium ion. And this hydration process refers to a coordination of water molecules around that particle. Solvation is the same process regardless of solvent. So if I was going to have an interaction of the solvent with some other solute, that would also be a coordination of those solvent particles in a similar way to what water does. For example, the sodium plus will coordinate with a number of water molecules where the negative ends of the water molecule and this polar oxygen will be aligned towards the sodium ion. Now, different degrees of solubility exist depending upon the nature of the overall solid versus dissolved ratio. Miscibility is a term that refers to dissolution of liquids in liquids rather than solids in liquids. It follows the same factors as a solid solute, where strong solute-solvent forces will favor dissolution, weak solute-solute forces will favor dissolution, and weak solvent-solvent forces favor dissolution. Usually, the solute is weaker in a liquid, so it tends to be more negligible than it is in a solid. This means that the cohesive forces overall are weaker, which will produce a more exothermic process if I were to compare the exact same heat of solvation to the crystal lattice energy or the solute energetics of the liquid. So we can use these properties to predict trends in solubility. The larger the difference in polarity between the solute and the solvent, the less likely it is going to be soluble, because the weaker the interaction is going to be between the solute and the solvent, which is going to weaken the heat of solvation. Excluding a gas, the higher the temperature is, usually the more soluble a substance will be as well. Because we're going to have a stronger adhesive interaction, we're also going to have more kinetic energy that will begin to break up those cohesive forces in the crystal lattice energy. For gases only, higher pressure tends to equal higher solubility. Looking at the rate of an actual dissolution, a dissolution process occurs faster with a larger surface area. So if I take something like a piece of rock sugar and try to dissolve it in a solution, it will not dissolve nearly as quickly as granulated sugar will, because the granulated sugar has a much higher overall surface area. Most of the rock sugar's particles are contained within the crystal, away from the surface. As a reaction occurs, or dissolution process occurs, the surface area will shrink because those particles that are on the surface will be removed and brought into solution. At the same time, the solution begins to fill up with particles. This slows the overall rate of dissolution. The point at which we have an equilibrium between those things which are dissolving and those things which are recrystallizing is a point at which the dissolution stops overall in terms of concentration changes. This is referred to the saturation point. So a substance is saturated when the equilibrium is established between its solid component and its dissolved component. The dissolution is going to be temperature dependent, so saturation will vary with temperature. You can actually supersaturate a substance by changing temperatures in relation to its saturation point. If I have a substance which dissolves at higher temperatures, more than at lower temperatures, I can dissolve more of the substance at high temperature. If I then lower the temperature in a very careful manner, I can actually create a solution in which I have more solute dissolved than I should be able to at equilibrium. A process of recrystallization relies on this supersaturation process in order to purify. What one does in this case is creates a solution in which the desired recrystallized substance is soluble at high temperature, but relatively insoluble at low temperature. You dissolve this substance at high temperature and let it cool. As it cools, it will begin to crystallize. The supersaturated solution will release its solute and become a solid form. This also occurs if you are able to create a supersaturated solution which has not yet precipitated if you were to agitate the solution, and that will cause the solute to come out. As the crystal forms, it tends to reject impurities because the structure will align in a more favorable way, and this causes a purification of the substance. Now, the dissolution process is temperature dependent. The direction of the temperature variation, whether the substance is endothermic or exothermic, will determine whether or not heating will increase or decrease solubility. If I have an exothermic process, increasing temperature will actually reduce solubility because heat is a product which will tend to then favor reactants. If I have an endothermic process, increasing temperature will favor solubility because heat is a reactant, which will then favor product in the equilibrium. Soluble gases and liquids of approximately the same polarity will reach equilibrium. If I have oxygen, for instance, it can dissolve in water. Gas dissolution is a very exothermic process, so it tends to lose solubility as temperature increases. Henry's law refers to the pressure relationship in a gas, where the number of moles of gas in a solution that are soluble are proportional to the partial pressure of that gas that is in contact with the liquid. So the concentration on the left is equal to a constant times the partial pressure of the gas above the liquid on the right. The constant itself depends upon the particular gas as well as the solvent it's dissolving in and the temperature. The caveat is, for Henry's law to apply, the gas cannot react with the solvent that it's dissolving in. For example, carbon dioxide in soda is bottled under high atmospheric pressure, so the pressure of carbon dioxide above the solution is much higher. This causes more carbon dioxide to be able to be dissolved. When you open the can of soda outside of the factory, it is now exposed to the actual atmosphere, which has a much lower concentration of carbon dioxide, partial pressure-wise. And so the overall solubility is decreased, which means that the excess carbon dioxide will escape. Colloids versus solutions versus suspensions. If I have a clear liquid that can be either a pure substance, a true solution, or a colloid, which it is based on its composition and particle size. If it is simply one substance, it's a pure substance. If its particle size is less than 1 nanometer, it's a solution. If the particle size is between 1 and 200 nanometers, it is a colloid. Other suspensions can exist which are greater than 200 nanometers, and these are just simply called suspensions or precipitates. A colloidal suspension is an even distribution of these particles in a mixture. It looks clear, but we can actually determine a difference between a colloid and a solution through what we call the Tyndall effect. The Tyndall effect is a process by which light scatters off the colloid particles. The solution particles are too small to cause light scattering, but the colloid particles can scatter light. We see this process if you shine headlights into a fog, or if you shine a laser through a room with dust in it, you can see the laser because of the scattering of light. Now, some colloidal properties are that they have a high particle surface. This is because the particles are small and widely distributed. Particles other than the suspension can actually adsorb to the mixture of the suspension, which means that they will stick to the colloidal suspension, and they will produce what we call sols, or solid dispersed in liquid. There are two different types of colloids, hydrophobic and hydrophilic. Hydrophilic colloids are like water. Things like proteins, for instance, will form sols, these solids dispersed in liquids, by folding to hide the hydrophobic parts and then being suspended throughout the solution. A cell will form a gel or a network of solid that encloses its dispersing medium, in this case the cytoplasm. Hydrophobic things are things like milk, fat dispersed in a polar solvent. They require an emulsifier which will coat the hydrophobic surface to allow it to disperse. This is the only way that milk is able to have the fat distributed in it. You see the same thing with Italian dressing, where the vinaigrette is dispersed in, the oil is dispersed in vinaigrette.